Good morning. Today we're going to learn about fan blowers and compressor. So what is a fan blowers and compressor? It's a gas moving machinery comprises mechanical devices used for compressing and moving gases. They are often classified or considered from the standpoint of the pressure head, and they include fan for low pressure, blower for intermediate pressure, and compressor for high pressure. That is the category for fan blowers and compressor. Fans the most common method for moving small volume of gas at low pressure is by means of a fan. This is example of a fan. Large fans are usually centrifugal and their operating principle is similar to that of centrifugal pump, which we have learned last week. The discharge heads are low from 0.1 to 1.5 meter H2O. However, in some cases, much of the added energy of the fan is converted to velocity energy and a small amount to the pressure head. In a centrifugal fan, the centrifugal force produced by the rotor causes a compression of the gas called the static pressure head. Also, since the velocity of the gas is increased, a velocity head is produced. Both the static pressure head increase and velocity head increase must be included in estimating efficiency and power. Operating efficiency are in the range 40 to 70%. If you need to estimate it is within this range. The operating pressure of a fan is generally given as inches of water gauge and is the sum of velocity head and the static pressure of the gas leaving the fan. Incompressible flow theory can be used to calculate the power of fan. Example: it is desired to use 28.32 meter cube per minute of A metered at a pressure of 101 kilopascal and 294 Kelvin. In the process, this amount of A, which is at rest, enters the fan suction at a pressure of 741.7 mmHg and a temperature of 366.3 Kelvin and is charged at a pressure of 769.6 mmHg and the velocity of 45.7 meter per second. A centrifugal fan having a fan efficiency of 60% within the range of 40 to 70 is to be used to calculate the brake kilowatt power needed. Incompressible flow can be assumed since the pressure drop is only 27.9 over 741.7 times 100 or 33.8% of the upstream pressure. So 27.9 we get it from 769 minus 741. The discharge pressure and the suction pressure. The average density of the flowing gas can be used in mechanical energy balance equation. So to use mechanical energy balance equation, you need to find out few terms like rho 1, which is density and suction point 1. Rho 2 is the density and discharge point 2. This is the raw average and the flow rate of the gas. So to start with raw 1 to 28.97 kilogram per kilogram A over kilogram mole is obtained from this is a molecular weight of air from appendix A1. You may refer to Gian Copley's book. Then 1 kilogram mole over 22.414 meter cube is volume of the A. 273.2 over 366.3. 266.3 is suction temperature. This is atmosphere temperature. 741 is the suction pressure. This one is ATM is in mmHg. So you get 0.94 kilogram per meter cube. So using the row 1, you can calculate the row 2, while the pressure is 769 over 741, which is suction and discharge pressure. You get 0.97 kilogram per meter cube, and the average is 0.958 kilogram per meter cube. The mass flow rate of the gas is m equal to 28.32 from the question. This is a unit conversion. This is from appendix A1 here. Volume of A. And 273 is the temperature atmosphere at the suction. Point 1, 294 is the suction is the A. It is desired to use mean of A, okay. 28.97 is molecular weight of air from appendix A1, so you get 0.5663 kilogram per second. Once you obtain that, then you can calculate the developed pressure head, which is rho 1 minus rho 2 over rho AV. No, pressure at point 2 minus pressure at point 1 over rho AV. Yeah, rho AV. Okay, not rho AV. Okay. So 769.6 minus 741.7. So this one to change it to ATM. Yeah. Unit conversion. And this is a raw average. So you get a developed pressure head of 3,883 joule per kilogram. The developed velocity head for V1 is 0. But for V2, here, although this is process program for of a pump, but the mechanical energy balance equation is derived from a pump. So V2 velocity at point 2 here, divided by 2, 45.7 given in the equation. The power of 2 over 2 is 1044 joule per kilogram. Then this is the mechanical energy balance equation. Z1 is here, Z2 is at point 2, V1 0.1, rho 1 is 0.1 as well. So here you can see Ws is mechanical energy, joule per kilogram. Sigma F is friction loss. This okay. So setting Z1 equal to 0, Z2 equal to 0, V equal to 0. So Z1 and Z2 is 0 because there is not given in the question. So we can assume it as 0. Maybe it's the way the, the, the fan is designed, in which the datum for Z1 and Z2 is similar. So friction loss is 0, assume negligible in solving for mechanical energy. So minus Ws equal to rho 2 P2 minus P1 over rho AV plus V2, which is the developed velocity for V2 over 2, 3,823 plus 1,044. We get 4927 joule per kilogram for mechanical energy. Substituting into equation 7.1-2 to calculate the brake kilowatt. This is the equation. Minus WSM is mass flow rate. Yeah. Over, this is efficiency 0.6, 0.6%, 60%. So you will get 4.65 kilowatt or 6.23 horsepower. So the brake kilowatt power needed for this fan is 4.65 kilowatt.